There's a photon of light inside the sun right now that has been traveling for over 100,000 years, and it still hasn't escaped. It began its journey in the burning core of our star, born from a nuclear collision between two hydrogen nuclei at a temperature of 15 million degrees. And yet, despite moving at the speed of light, it has been bouncing and scattering through the solar interior for so long that ancient human civilizations rose, collapsed, and vanished entirely while it was still wandering through the inside of the very star we see every day. That single fact, more than almost anything else, tells you something profound about how strange and how deep our sun truly is. We live in the light of a star, but we have never truly seen the star itself. We see only its surface, and the surface is a lie. For most of human history, the sun was simply the sun. It rose, it set, it gave warmth and governed the seasons. Even once we understood that it was a star, a colossal ball of plasma held together by its own gravity and powered by nuclear fusion, it remained largely unknowable from the inside. You cannot send a probe into the sun the way you might send one to Mars. You cannot drill into it or take a sample. It is, by almost every measure, the most inaccessible object in our solar system, not because of its distance, but because of its violence. And yet, in just the last few years, humanity has done something that would have seemed like science fiction to every generation before us. We have looked deeper into the sun than ever before, and what we have found is rewriting everything we thought we knew. To understand just how layered and secretive the sun really is, you need to picture it from the inside out. At its very center lies the core, a region roughly the size of Jupiter, where the pressure is 340 billion times greater than the air pressure at sea level on Earth. Inside that almost incomprehensible environment, hydrogen nuclei are forced together so violently that they fuse into helium, releasing staggering amounts of energy in the process. This is the engine. This is where every photon of light that will eventually warm your face on a sunny afternoon is first born. But it is born into a prison. The core is surrounded by an enormous region called the radiative zone, a dense sea of plasma that photons cannot travel through in a straight line. Instead, they scatter, bounce, and deflect, moving only tiny fractions of an inch before crashing into another particle and changing direction entirely. This random walk through the radiative zone is so tortuous, so maddeningly indirect, that scientists estimate it takes light between 100,000 and 1,000,000 years to travel from the core to the outer edge of this region. Compare that to the 8 minutes it takes sunlight to travel from the sun's surface to the Earth across 93 million miles of empty space, and the sheer density of the solar interior becomes almost incomprehensible. Above the radiative zone lies the convection zone, where energy finally begins to move differently. Rather than passing photon by photon through dense material, huge columns of hot plasma rise upward like boiling water in a pot, carrying energy toward the surface before cooling, sinking back down, and rising again in an endless churning cycle. This is the layer that drives many of the sun's most visible behaviors. The granules you can see on the solar surface through a powerful telescope, those cell-like structures roughly the size of Texas, each one a single convective column of rising and falling plasma. And above all of that sits the photosphere, the visible surface, the thin layer from which light finally escapes into space. When you look at the sun, shielded through a solar filter, the photosphere is all you see. It is roughly 500 kilometers thick, a vanishingly thin skin stretched over a star that is 1,400,000 kilometers in diameter. Everything below it is hidden, or at least it was. The first breakthrough in seeing through that surface did not come from a rocket or a telescope in the traditional sense. It came from sound. In the 1960s, scientists discovered something puzzling about the sun's surface. It was vibrating. Not obviously, not visibly, but constantly and rhythmically, oscillating in complex patterns with a dominant period of around 5 minutes. At first, this seemed like a curiosity of the solar atmosphere, perhaps some local turbulence near the surface, but over the following decades, scientists realized these were not surface ripples. They were the visible expression of sound waves, acoustic pressure waves, resonating through the entire interior of the sun, bouncing between the surface and the deep interior, the way sound waves bounce around inside a musical instrument. The sun, it turned out, was ringing like a bell. And if you could read those vibrations carefully enough, you could decode what was happening deep inside. This field became known as helioseismology, a direct parallel to how geologists use seismic waves from earthquakes to map Earth's interior. By analyzing the precise frequencies, amplitudes, and patterns of the sun's oscillations, scientists were able to construct detailed maps of the sound speed and density at different depths throughout the solar interior. Inverting these measured frequencies, helioseismologists constructed detailed maps of the sound speed and density throughout most of the solar interior, revealing the precise locations of key internal boundaries, such as the base of the convection zone, and providing stringent tests of solar structure models. They discovered that the sun rotates differentially. Its equator spins faster than its poles, and that this differential rotation persists all the way through the convection zone, but then abruptly transitions to a more uniform rotation deeper down. They identified the exact depth at which the radiative zone meets the convection zone, and they did all of this without ever going inside. They did it by listening. One of the greatest triumphs of heliosismology came with what was called the solar neutrino problem. For decades, experiments detected far fewer neutrinos streaming out of the sun's core than the standard theoretical model of solar physics predicted. Neutrinos are almost impossibly elusive subatomic particles produced in enormous quantities by the nuclear fusion reactions in the sun's core and passing through virtually everything, including the entire Earth, as if it were not there. 1 trillion solar neutrinos are passing through your body every second as you sit or stand wherever you are right now. But the measured flux, the number actually detected, was consistently far lower than expected. Either our understanding of the sun's core was wrong, or our understanding of neutrinos was wrong. A major early triumph of heliosismology was its solution to this problem, showing that the sun's core properties were consistent with nuclear physics, and that the missing neutrinos must be due to new neutrino physics. The sound waves confirmed that the sun's interior was exactly as the models described. The problem was, with the neutrinos themselves, they were transforming or oscillating between different types as they traveled, becoming invisible to the detectors that could only see one variety. It was one of the first discoveries in history where looking into the sun helped us understand something fundamental about the very building blocks of matter. The sun became a physics laboratory. More recently, in 2025, a novel helioseismic method inferred the solar radiative opacity directly, finding it about 10% higher than theoretical values in a region deep within the sun. This matters enormously because the opacity of solar material, how resistant it is to the passage of radiation, is one of the key factors that determines the structure of the entire star. A slight discrepancy here propagates outward into almost every calculation we make about how the sun is built. Scientists are still working to understand whether this points to gaps in our models of atomic physics or something else entirely about the solar interior. The deep sun, even now, is still offering surprises. But heliosismology can only go so far. Sound waves give us a statistical, averaged picture of the interior. They cannot show us the real-time dynamics happening at the surface and in the lower atmosphere of the sun with any granularity. For that, you need to go there, and that is precisely what NASA set out to do. The Parker Solar Probe was launched in August 2018, named after Eugene Parker, the astrophysicist who first mathematically predicted the existence of the solar wind in the 1950s. A prediction that was widely dismissed at the time, but later confirmed by early space missions. Parker himself lived to see his namesake spacecraft launch and to learn about its early discoveries before he passed away in 2022 at the age of 94. The probe was built around one central, audacious ambition: to fly into the sun's outer atmosphere, the corona, and make measurements from within it, to touch the sun. This required solving an engineering problem that, frankly, sounds impossible. The corona reaches temperatures of 1 to 3 million degrees Celsius. The sun's surface below it is a comparatively mild 5,500 degrees. Yet the probe needed to survive in that million-degree environment without melting. The solution was a carbon composite heat shield roughly 12 centimeters thick, engineered to withstand temperatures of up to 1,400 degrees Celsius on its sun-facing side, while keeping the instruments it protected at roughly room temperature. The shield works partly because, while the corona is extraordinarily hot in terms of the energy of its individual particles, it is also extraordinarily thin. There simply aren't very many particles in the corona at any given location, and so even though each one carries enormous energy, the total amount of heat transferred to the spacecraft is manageable if the shield is thick and the right shape. The probe spiraled inward over 6 years, using gravity assists from Venus to gradually tighten its orbit around the sun on a series of increasingly close passes. In 2021, it became the first spacecraft to fly through the sun's corona, allowing it to effectively touch the sun. Then, on Christmas Eve of 2024, it achieved something that no human-made object in history had ever done. Parker Solar Probe started its closest approach to the sun on December 24, 2024, flying just 3.8 million miles from the solar surface. To put that distance into perspective, Mercury, the closest planet to the sun, orbits at an average distance of 36 million miles. Parker was nearly 10 times closer than that. If the distance between Earth and the sun was the length of an American football field, the spacecraft would have been around 4 yards from the end zone. It was hurtling through the solar atmosphere itself, inside the corona, closer to the surface of a star than anything humanity had ever placed. At a blistering speed of 430,000 miles per hour, the spacecraft soared within 3.8 million miles of the sun's surface, breaking its record for both proximity and speed. That speed, 430,000 miles per hour, is fast enough to travel from one side of the Earth to the other in roughly 2 minutes, fast enough to circle the moon in less than 30 seconds. It is the fastest any human-made object has ever moved. And the reason it needs to move that fast is not engineering ambition, but simple physics. At that distance from the Sun, the star's gravitational pull is so immense that the probe must move at that extraordinary velocity just to maintain orbit rather than being dragged inward. On the night of December 26th, controllers at the Johns Hopkins Applied Physics Laboratory received a beacon signal from the probe confirming it had survived the passage. The data itself came in on the 1st of January 2025, and what it contained has kept scientists busy ever since. The new images captured by the Wide Field Imager for Solar Probe, or WISPR, reveal the corona and solar wind, a constant stream of electrically charged particles from the Sun that rage across the solar system. But these weren't just pictures in the conventional sense. They were views from inside a stellar atmosphere, showing the corona in motion, showing the solar wind being born, and showing structures and phenomena that we had only theorized or glimpsed from afar. One NASA official described the mission as allowing scientists to witness where space weather threats to Earth begin, with their eyes, not just with models. Among the most striking findings involve structures called switchbacks. These are abrupt, S-shaped kinks in the Sun's magnetic field lines, places where the field briefly reverses direction before snapping back. The probe had previously found that switchbacks are incredibly common in the solar wind, not a rare occurrence as previously thought. Scientists initially considered them prime candidates for explaining the corona heating mystery, a long-standing and genuinely baffling puzzle at the heart of solar physics. Why is the Sun's outer atmosphere so much hotter than its surface? Think about that for a moment. Imagine standing a few feet from a bonfire. You feel the heat. Now imagine walking away from the bonfire and suddenly finding that the air gets dramatically hotter the farther you move away. That is essentially what happens with the Sun. Its surface sits at around 5,500 degrees Celsius, but the corona, the wispy outer atmosphere that stretches for millions of miles, is millions of degrees. Energy cannot spontaneously flow from cooler to hotter regions according to the basic laws of thermodynamics. Something must be actively heating the corona from below. But what? After analyzing data from Parker Solar Probe's first 14 passes around the Sun, researchers discovered that while the S-shaped switchbacks are common in the solar wind near the Sun, they are absent from inside the corona itself. This was a critical finding. If switchbacks originated in the corona and heated it, you would expect to find them there. Their absence inside the corona suggests they form somewhere in the transition between the solar surface and the corona, which means they are probably a consequence of whatever is heating the corona rather than the cause. One popular theory now involves a different kind of wave entirely. In October 2025, scientists announced direct evidence of small-scale torsional Alfvén waves in the Sun's corona, observed using advanced spectropolarimetric techniques with the Daniel K. Inouye Solar Telescope in Hawaii. Alfvén waves are oscillations that travel along magnetic field lines the way waves travel along a vibrating guitar string. They were first theorized in the 1940s, and for decades, scientists suspected they might be responsible for heating the corona. But actually detecting them in the right location with the right properties to explain the heating had proved frustratingly elusive. These newly observed waves may also explain the magnetic switchbacks detected by Parker Solar Probe, and as one researcher put it, having direct observations finally allows scientists to test theoretical models against reality. Then, in the middle of 2025, Parker's data produced another revelation. Scientists detected evidence of a previously theoretical structure called the helicity barrier, a phenomenon that occurs when magnetic turbulence in plasma becomes so twisted that it prevents energy from dissipating normally. Instead of simply fading into heat, the magnetic energy gets recycled in complex ways, possibly explaining why the corona remains so intensely hot. It was described as though the Sun's atmosphere has its own internal recycling system for magnetic chaos, one that keeps energy trapped in the corona rather than letting it escape. This discovery is not just relevant to the Sun. Understanding how plasma behaves in extreme magnetic environments has implications for our understanding of everything from other stars to the environments around neutron stars and black holes. The December 2024 flyby also gave scientists their clearest views yet of coronal mass ejections, massive eruptions of charged particles in magnetic fields blasted from the Sun's surface that can travel across the solar system and slam into Earth's magnetic field, triggering geomagnetic storms. Among the most remarkable images were views of multiple coronal mass ejections captured in high resolution, with scientists observing these enormous explosions basically piling up on top of one another. When coronal mass ejections collide in space, they can change direction, merge magnetic fields, and accelerate energetic particles in ways that make them far more dangerous to Earth's technological infrastructure than a single ejection would be. Understanding how they merge and interact is crucial for improving space weather forecasts. Images published in the astrophysical journal Letters revealed that not all magnetic material in a coronal mass ejection escapes the sun. Some makes it back, changing the shape of the solar atmosphere in subtle but significant ways that can set the course of the next eruption to leave the sun. The sun, in other words, has a kind of feedback mechanism built into its eruptions. Each explosion changes the conditions for the next one. The corona is not a passive structure that just sits there while eruptions punch through it. It responds, reforms, and sets the stage for future events. The slow solar wind, which moves at a more leisurely 220 miles per second, remains one of the biggest mysteries in heliophysics. It appears there are two different kinds of slow solar wind. One called Alfvénic, which shows small magnetic fluctuations like switchbacks, and a second non-Alfvénic type that doesn't. Thanks to Parker Solar Probe's close flybys, scientists have confirmed that both types exist and are gathering clues about where they originate. Early evidence suggests the non-Alfvénic slow wind may come from vast, arching loops of solar material called helmet streamers. These are enormous magnetic structures visible during total solar eclipses, stretching out from the sun's equatorial regions like pointed helmets. That the slow solar wind might be anchored there, funneled outward through these structures, is a tantalizing lead in one of the longest-standing puzzles in heliophysics. And Parker is not finished. It will continue making ever closer passes through the sun's corona. And with each swoop, the probe gathers unprecedented data about how the sun works and, by extension, how it affects every planet in the solar system, including Earth. The data flowing in from this single spacecraft has already forced textbook rewrites, confirmed long-theorized phenomena, and raised entirely new questions. That, perhaps more than any individual discovery, is the hallmark of truly transformative science. What makes all of this so philosophically staggering is the intimacy of it. The sun is not a distant, abstract object in the universe. It is our star. Its light grew the first plants on this planet. Its warmth drives our weather, our seasons, our oceans, our atmosphere. Every calorie of energy in every living thing on Earth traces back to nuclear reactions happening right now, this very moment, in a core we are just beginning to understand. The photon that left the sun's core 100,000 years ago might be arriving at your window this afternoon, and between its birth and your morning, entire civilizations came and went while it was still ricocheting through the interior of our nearest star. We have probed that interior with the mathematics of sound waves. We have flown a spacecraft directly through the star's outer atmosphere at 430,000 miles per hour on Christmas Eve, and received a message back saying it survived. We have, for the first time in history, watched the solar wind being born in real time, seen eruptions collide in the corona, and detected the waves that may finally explain the million-degree mystery that puzzled scientists for generations. We have looked deeper into the sun than any instrument, any mission, any generation before us has ever managed to look. And still, buried far below everything we can reach, the core continues its ancient work in silence, crushing hydrogen into helium, producing neutrinos that slip through the entire Earth as if it were not there, generating light that will take 100,000 years to find its way out. The sun keeps its deepest secrets behind barriers of temperature and density that no physical object will ever penetrate. But we are learning to read the signals it sends upward, learning to hear it, learning to feel it, learning to fly through its very atmosphere. Each orbit of Parker Solar Probe, each resonating oscillation mapped by helioseismologists, each torsional Alphen wave finally captured by a telescope in Hawaii. All of it is us getting just a little closer, learning just a little more about the star, without which none of us would exist. And that, somehow, makes the morning light look different.